Hi everyone, this is Wenhui, and this is my final project presentation. And since I have some problem of running OpenCV on my MacBook, so I cannot plot the map or plot the menu, so I will show the tests that I passed using Basel test in the following slides. Okay, for step 1, this is about autocomplete. I first traverse all the nodes and then transform the characters to lowercase because this is not case sensitive, and then check if the node name contains the provided string and return all the node names. The runtime complexity for autocomplete is big O of n. And for this step 2, this is about finding the position of the node. And I first traverse all the nodes and check if the node name matches, and then get the latitude and the longitude and return the position. The runtime complexity is also big O of n. And you can see in this figure that for each task there are 4 tests, and I passed all the tests for each task, and the time taken to finish each task is pretty short because this is a very simple algorithm. And step 3 is about calculate shortest path, and there are 2 algorithms, Dijkstra and Bellman-Ford. So for Dijkstra algorithm, I used mean heap to optimize this algorithm, and the time complexity can reduce from big O of n squared to big O of n plus m in log of n, where n is the number of nodes and m is the number of edges. And for Bellman-Ford, I do relaxation on all the edges for all the nodes in the graph, and the runtime complexity for Bellman-Ford is O of n times m. And you can see in the figure the test results that the time taken to finish Bellman-Ford is always longer than the time taken to finish Dijkstra. This is because Dijkstra is more optimized and it is faster according to our runtime complexity analysis. And for step 4, this is about solving TSP. And first I implemented the brute force algorithm. And for brute force, this is quite straightforward. I perform DFS to find the permutations, all the possible permutations, and calculate the path length and record the shortest path length and return the results. And the time complexity is big O of n factorial. And in the figure showed 3 tests that I run with my program, and I passed all the 3 tests, and from test 1 to test 3, the number of nodes increases, and you can see that as the number of node increases, the runtime also increases. Also, for brute force solution to TSP, I found something interesting. So instead of using DFS to generate permutations, I used a STL function to generate the permutation, and this STL function is called next permutation. And by using this STL function, I found out that the time taken to finish the task decreased a lot compared to the one implemented with DFS. Okay, and this is the backtracking implementation of TSP. And for backtracking algorithm, we just added early backtracking to save time. We just modify a few lines in the original DFS function. So if the current path length is greater than the current minimum, then return. So that will save us a lot of time. And the time complexity is still big O of n factorial. And here is the 2OPT TSP. So the general idea here is to swap two locations and calculate the new total cost to check if there's improvement. So if the improvement of distance after each iteration is less than epsilon, we stop the loop and finish the task. I did some interesting experiments on 2OPT TSP, and the time complexity for 2OPT is big O of n squared. So the value of epsilon, the choice of epsilon is kind of interesting. If we set epsilon to 0.01, so my program couldn't find optimal value within 5 minutes, so it will print out a timeout message like in this figure showed. And if I set epsilon equals to 0.1, then it can find optimal value. And I tested two different cases. And in the first case, the difference between my path length and ground truth path length is 0.74. And in this case, my path length, the difference from my path length is from ground truth path length is 1.086. So here is the runtime comparison of between the three algorithms. So we can see in this table that 2OPT runtime is always the smallest, because 2OPT has the simplest time complexity. It's O of n squared, while the other two is O of n factorial. And as we can also see that with the number of nodes increasing, the runtime also increases. Of all the three algorithms, it all increases. And when the number of nodes is large, the backtracking runtime is better than brute force. But when the number of nodes is relatively small, the backtracking is approximately the same as brute force runtime. So I think we should use more nodes to show the difference between the different algorithms. And also the runtime also relevant to computer states, like whether there are other tasks running at the same time, it can make a difference to the runtime. Okay, for step 5, this is about detecting cycles in the subgraph. So I used DFS to detect cycles, and the time complexity is big O of n plus m. So it is just the total number of edges and nodes in the graph, because we need to traverse all the nodes and edges. And in this figure, you can see that there are two tests for this task. The first test shows that there exists cycle in the subgraph, while the second test shows that there exists no cycle in the subgraph. Step 6, delivering Trojan. So this is about topological sort. To implement topological sort, I first construct a DEG and then perform DFS to get topological list. And the time complexity here is also big O of n plus m, the total number of edges and nodes in the graph. And in the figure, I showed that I also successfully implemented these two functions, read locations from CSV file, read dependencies from CSV file, because I cannot run OpenCV, I cannot plot the menu and the map. So I want to show in the test that I also successfully implemented these two functions. I can read locations and read dependencies from CSV file, and I also passed this test. Step 7, key closest locations. So this is about find key nearest neighbors problem. I used a max heap to keep key locations. So if the location distance is smaller than the heap top value, so we pop out the heap top and then push this location into the max heap. So after traversing all the nodes, the max heap will have the key smallest values. And in the figure showed my test. So this is the 10 nearest locations to Ralph's. Other than the location names, I also printed the distances of these locations to Ralph's. Okay, that's all. Thank you.